This video is a speculative thought experiment built on real geology, real physics, and real science. The specific void described does not exist. What I'm about to describe has not happened. I want to be clear about that up front. But everything that makes it possible, the physics, the geology, the technology, is completely real. And scientists who study the deep Earth will tell you that a discovery like this is not impossible. It is just one we have not made yet. So here is the scenario. Imagine that tomorrow, a research vessel in the North Atlantic gets an anomalous reading on its sonar. The seafloor beneath it looks wrong. The signal is dropping into something it cannot resolve. Something deep, wide, and structurally unlike anything in the surrounding crust. A team of geophysicists pulls the satellite altimetry data for that coordinate and finds what they were afraid to find. A dip in sea level directly above it. Not 100 meters. More. And when they run the numbers on the size of what the sonar is showing them, one of the researchers says quietly that the opening alone could swallow the island of Manhattan. What happens next? To the science, to the politics, to our understanding of the ground we are standing on, is what this video is about. First, let's understand what we are actually talking about. Manhattan is roughly 13 miles long and 2 miles wide. 23 square miles of bedrock, skyscrapers, 1.6 million people, 8 million tons of infrastructure. It sits on some of the most studied geology in the world, the Manhattan Schist, a dense metamorphic rock that has been holding up skyscrapers since 1902 and was stable long before that. The void in our scenario has an opening roughly 15 miles across. That means the entrance alone, before you even get to whatever is inside, is wider than Manhattan is long. If you lined up the Empire State Building, the Chrysler Building, One World Trade, and every skyscraper in between end to end and dropped them into the opening, they would disappear inside it with room to spare. At the depths we are talking about, several kilometers below the seafloor, which is itself several kilometers below the ocean surface, the pressure is extreme. Every 10 meters of water depth adds roughly 1 atmosphere of pressure. At typical abyssal depths, that is already 400 to 600 atmospheres. Deep sub-sea floor cavities would exceed anything conventional submersibles are rated for. The Titan submersible, which imploded in 2023 while descending toward the Titanic at around 3,800 meters, was operating near the edge of what human engineering currently handles. The void in this scenario sits deeper, so we know it is there from the data. We cannot go inside it. Not yet. And what we can see from the outside is already enough to make geologists very uncomfortable. Here is how something like this would actually be detected. We do not discover deep geological structures by drilling to them. Drilling into the Earth is extraordinarily difficult. The deepest borehole ever made, the Kola Super Deep Borehole in Russia, reached just 12 kilometers after 24 years of work and was eventually abandoned when the rock got too hot and began closing around the drill. 12 kilometers sounds deep. The mantle begins at about 35 kilometers. We have never reached it. Instead, we read the deep Earth indirectly. Gravity sensors on satellites measure tiny variations in gravitational pull across the surface of the planet. Where there is more mass, denser rock, thicker crust, gravity is slightly stronger. Where there is less mass, a cavity, a low-density intrusion, a void, gravity is slightly weaker. And that weakness shows up as a dip in the geoid, the technical term for the gravity-defined shape of the Earth's surface. This is not hypothetical technology. The GRACE satellite mission has been mapping global gravity variations for over 2 decades. The Indian Ocean geoid low, a real gravitational anomaly almost the size of India, was confirmed and studied using exactly this method. The ocean surface above it sits 106 meters lower than surrounding water because gravity there is genuinely weaker. A large sub-sea floor void would produce a similar signature. Less mass below means weaker pull, above means a measurable dip in sea level. The signal would be subtle, the anomaly buried under kilometers of rock and water. But modern satellite altimetry is sensitive enough to detect it. And once a research team noticed the dip and cross-referenced it with sonar bathymetry showing anomalous seafloor returns, the picture would start to come together. That is how you find something like this without ever going near it. Now the harder question. How does something this large exist inside the Earth without collapsing? The short answer is that large voids do exist in the Earth's crust. We know this because of caves. Hang Son Doong in Vietnam is large enough to contain a 40-story building inside its main chamber. Lava tubes on the Moon and Mars stretch for hundreds of kilometers. On Earth, massive underground chambers have formed through a combination of dissolution, where acidic water slowly dissolves soluble rock over millions of years, and structural collapse, where ancient tectonic activity fractures the crust and leaves open spaces. Sub-sea floor voids are harder to study but are known to exist. Oceanic crust contains extensive void networks, channels, chambers, and fractures through which seawater circulates and interacts with hot rock in a process that generates unique chemical signatures and supports entire ecosystems of chemosynthetic life. What would make a void of this scale unusual is not that it exists. It is the combination of its size, its depth, and its apparent structural stability. A cavity 15 miles across, sitting multiple kilometers beneath the seafloor, would need to be an extremely hard, coherent rock, likely ancient basaltic crust that cooled very slowly and developed exceptional compressive strength. Alternatively, geophysicists would consider whether the void's geometry itself is helping it stay open. Arched structures, the same principle behind a stone bridge, distribute load and can remain stable under enormous weight for very long periods. The chemical signatures leaking from the void's floor would be one of the first things scientists would want to analyze. If hydrothermal gases, hydrogen sulfide, carbon dioxide, methane, were escaping from cracks in the lower structure, that would suggest a connection to deeper heat sources. It would not prove a link to the mantle, but it would raise the question. This is where the scenario stops being just scientifically interesting and starts being geologically consequential. Tectonic plates are not rigid slabs moving smoothly through space. They are under constant stress, being pushed from spreading ridges, pulled by subducting edges, twisted by friction against neighboring plates. The North American plate, specifically, is under a complex stress regime from multiple directions. The Mid-Atlantic ridge is spreading. The Cascadia subduction zone on the west coast is locked and building strain. The New Madrid seismic zone in the interior is an ancient failed rift still producing earthquakes. A void of significant size sitting beneath the plate would add a new variable to that stress picture. Not a catastrophic one on any immediate timescale. Geology moves slowly. But a large cavity beneath oceanic crust adjacent to a continental margin creates what geophysicists call a stress concentration, a point where the surrounding rock is bearing load that the void is not, and where fractures propagate preferentially. The specific concern in this scenario would be seismic shadowing. When an earthquake occurs, it sends waves through the earth in all directions. Seismologists use the pattern of those waves, which arrive where, how fast, how distorted, to build pictures of what is inside the earth. A large void disrupts that picture. Waves travel differently through an air-filled cavity than through solid rock. Depending on the void's geometry and position, it could create a blind spot in seismic monitoring networks, a zone where the arrival of certain wave types is delayed, absorbed, or deflected in ways that make it harder to detect and locate earthquakes nearby. This is not a dramatic threat. It is a calibration problem. But for early warning systems designed to give coastal populations minutes of notice before a tsunami, calibration problems matter. Here is where the scenario becomes genuinely interesting from a human perspective. The discovery of something like this in 2026 would immediately raise a jurisdictional question. The void in this scenario sits in international waters, technically under no nation's control. But if it turns out to be located beneath or adjacent to a continental shelf, territorial claims become complicated. The United Nations Convention on the Law of the Sea gives coastal nations rights over resources within 200 nautical miles of their shores, and potentially further if they can demonstrate that the continental shelf extends that far. A void of this scale, potentially connected to hydrothermal systems, potentially sitting above economically valuable mineral deposits, sitting in a geologically sensitive position relative to a major tectonic plate, that is, a scientific object, a potential resource, and a geopolitical flashpoint all at once. The response, realistically, would be a coordinated international science mission. Autonomous underwater vehicles, robotic drones that can operate at extreme depth without the life support constraints of a crude submersible, would be the primary tool. Modern AUVs like those operated by MBRI and the Woods Hole Oceanographic Institution can descend to 6,000 meters, map with centimeter-scale sonar resolution, collect water and rock samples, and transmit data in near real time. A coordinated swarm deployment, multiple vehicles mapping simultaneously from different angles, would give scientists the first real picture of the void's interior geometry. What they would be looking for, above everything else, is the structural ceiling, the underside of the rock spanning the void, because that is the variable nobody can model with confidence from the outside, how thick it is, how coherent, and what would happen to it under continued stress. Here is the thing about this scenario that I want to leave you with. Every piece of physics in this video is real. Gravity anomalies detected by satellites, real. Seismic shadowing from subsurface voids, real. Stress concentration around crustal cavities, real. AUV swarm deployments for deep ocean mapping, real. The Indian Ocean already has a gravity hole almost the size of India that sat unexplained for 75 years. The specific void in this video does not exist, but the Earth is a place where 80% of the ocean floor has never been mapped in detail, where the deepest we have ever drilled is 12 kilometers into a crust that is 35 kilometers thick, where we are still finding new geological structures that force us to revise what we thought we understood about the planet. The honest answer to could something like this exist without us knowing is yes. Probably not exactly like this, but something down there that we have not seen yet, that the indirect signals have not clearly pointed to, that is waiting for the right instrument in the right place at the right moment. We are living on a surface. What is below it is mostly still a guess. If you want to go deeper into what we actually know about the real gravity anomalies we have already found, the ones that are confirmed, measured, and in some ways even stranger than this, watch our next video